Imagine engineering a spacecraft to survive re-entry, only to watch it shake apart because thrusters were bolted directly to the fragile life support system. Software behaves the same way under pressure. As applications grow in size, unmanaged dependencies between different parts of the code create massive structural friction. In a naive software architecture, objects rely directly on each other's concrete implementations. Every module is hardwired to the next, creating a tangled, rigid web of code. When you try to add a new feature or scale the system's capacity, the structure resists. Pulling on one operational thread risks snapping the entire architecture. What begins as a modular engineering project rapidly degrades into an unmaintainable, monolithic liability. In 1994, 4 engineers, known in the industry as the Gang of Four, published a manual to solve this exact problem. They formalized a concept called design patterns. Design patterns represent standardized, reusable blueprints for solving the most common structural flaws encountered in software design. The Gang of Four divided these blueprints into 3 core architectural intents: creational for instantiating objects, structural for assembling them, and behavioral for defining how they communicate. Beyond solving immediate coding errors, these patterns provide a universal language. A developer can instantly communicate a complex architectural idea to a colleague with a single term. We are going to put that taxonomy to the test. We will take a flawed, tightly coupled spacecraft simulation and use these patterns to refactor it into a robust, scalable system. Mastering these design patterns is the critical step to graduate from writing code that simply executes to designing systems that can scale indefinitely. Our first simulation requirement is straightforward. The system needs to calculate the total fuel consumption for individual ships and for entire fleets. Logically, when you think about it, a fleet is really just a larger group of individual ships flying together. But look at this initial architecture diagram. We have a specific object class for a ship and a completely separate disconnected class for a fleet. Because the ship and fleet classes do not share a hierarchy, the core application cannot process them uniformly. To run a simple fuel calculation, the main application logic is forced to use hard-coded instance of checks. The system has to manually inspect an object, verify if it is a single ship or an entire fleet, and then route it to a different calculation method. Relying on conditional type checks to manage object hierarchies violates the core principles of scalable, open-closed design. It breaks the moment you attempt to introduce a new type of unit. We solve this hierarchy friction with the composite pattern, a structural solution specifically designed to map part-whole hierarchies. The core metonic is simple. We define a single common abstraction that forces the client application to treat an individual object and a grouped composite object exactly the same way. We introduce a shared space unit interface. Both the ship leaf and the fleet composite inherit from it. Fleet now holds a collection of space units, allowing it to contain ships or subfleets. The application interacts entirely through this single interface, calling get fuel consumption. The composite pattern elegantly removes structural friction. It allows massive, deeply nested trees of objects to be operated on via one clean interface. Our second requirement introduces a problem of coordination. The simulation must execute a mission launch sequence, which requires checking the fuel, initializing the navigation array, and starting the engines. Looking at the naive code structure for this launch sequence, the main application has 3 direct, separate dependencies to the hardware subsystems. It's forced to understand their internal operations, manually calling check fuel, initialize route, and start engines in a rigid order. This lack of abstraction creates immense fragility. If the engineering team updates the internal engine system and changes how the startup sequence works, the entire high-level mission controller breaks. Forcing high-level application logic to manually orchestrate low-level subsystem operations is a recipe for rigid, unbreakable dependencies. We can shield the application from this using the facade pattern. This is a structural solution designed to provide a unified, simplified interface to a complex body of code. We refactor by inserting a new mission facade class directly between the main application and the 3 hardware systems. The subsystems remain untouched. Instead, the facade encapsulates the complex coordination and precise ordering of their methods. For the client application, the impact is immediate. It now only needs to know about a single operation: launch mission. We have drastically reduced its coupling to the back end. By establishing clean architectural boundaries, the facade pattern successfully hides localized complexity behind a robust, easy-to-use structural shield. The final simulation requirement is purely behavioral, reacting to mid-flight maneuvers by dynamically altering engine thrust and hull stabilization. If a sudden kinetic impact hits the hull, the system must instantly pivot thrusters and ramp up stabilization. But in the naive architecture for maneuver management, we see the application logic tightly coupled directly to the mechanical subsystems. The main application directly invokes specific hard-coded hardware commands, like increase thrust and increase stabilization. Because the action is executed the instant the method is called, the controller is paralyzed. It cannot cue these maneuvers, log them to reverse an action, or dynamically restructure the response mid-flight. When the decision of when to execute an action is permanently bound to the knowledge of how to perform it, behavioral flexibility is destroyed. We resolve this with the command pattern, a behavioral solution that decouples the invoker of an action from the object that actually performs it. We introduce a central command interface and concrete classes like increase thrust. These act as intelligent wrappers, storing a reference to the specific thruster system receiver. Finally, the main application passes the command to an actuator, which simply triggers it, without knowing what the command does. Because actions are now encapsulated as independent data objects, they can be stored in arrays, delayed, or swapped dynamically based on the telemetry of the ship. The command pattern achieves total behavioral decoupling, allowing you to parameterize clients with diverse, interchangeable operational requests. Consider the primary pitfall here: the misconception that adding more design patterns automatically makes code better. There is a fundamental trade-off. Every design pattern you apply inherently increases the structural complexity of the codebase by adding new interfaces, wrappers, and layers of indirection. If a pattern's added complexity shadows its actual architectural benefits, it is an anti-pattern for that specific codebase. If straightforward code cleanly solves your problem without introducing tight coupling, then forcing a pattern into the architecture is strictly unnecessary overhead. Engineering mastery requires the technical knowledge of implementation and the critical judgment to leave a pattern out entirely.